Okay, so in this session, we will learn about dynamic programming and how can we use this concept to solve problems. So, dynamic programming actually it stresses on storing already computed results because that can be reused. That's what dynamic programming says. So, it's nothing else than an advanced version of recursion. You can also call it as enhanced recursion. Now definitely we will see that how can we use this and how to identify this and all. For that I will take the example of Fibonacci. So let's say you are given with the problem of Fibonacci numbers. So I am sure that most of you are aware about it, that what Fibonacci problem is. So we have series, right? A Fibonacci series, and in that series we have like the 0, 1, and then 1, and then 2, and then 3, and then 5. So what Fibonacci sequence says is that if you want to find the ith number in Fibonacci sequence, it's given by sum of previous two numbers, or I can say that Fibonacci of the ith number in Fibonacci is sum of I minus 1th number and I minus 2th number. Now definitely it should exist. Now if you go and ask me that find for 0, I will do f of 0 and then I will do f of minus 1, but it doesn't exist. So yeah, that is always there. The check should be there that we will operate this formula only for I greater than 2 values, greater than or equals to 2. Otherwise, we will get negative values here, which definitely is not correct. We don't have uh, indexing from negative number. We have that from 0. So at least, at most, you can go till infinity theoretically, but at least it should be 0, right? So that check we have. And for 0 and 1, we do have these values fixed for us in the sequence, which are as follow. So Fibonacci sequence 0th number is always going to be 0 and first number it's always going to be 1. Now you may be wondering that it's a very simple problem, right? We just do recursion on it. Where's DP coming in this? And why do we think about even something else if we can do it with recursion? So there's a catch about it. So yeah, we'll discuss that. So in this case, you've seen that this specific thing, f of I is equals to f of I minus 1 plus f of I minus 2. This is nothing else than recurrence relationship. Okay, and in this question, you are given with recurrence relationship. However, uh, you may not get this recurrence relationship every time, and you may need to build it upon your own. The question may be in some story mode. Okay, so we have a question climbing stairs. Okay, if you will try to solve it, you will see that it's actually this thing only, same recurrence relationship, but you need to form it on your own. Okay, so recurrence relationship is nothing else. It's just it just expresses the solution of solution of a problem in term of smaller sub problems. In this case, I can say that if I want to find ith uh, number in Fibonacci sequence, it's dependent on I minus 1th number and I minus 2th number. Now to find I minus 1, it's a separate problem in itself. Okay, it's very independent problem. So I need that and I also need I minus 2. So whenever I need multiple sub problem and I aggregate somehow the result, here I'm not using the word sum to generalize it. You may do some max operation, min operation. Okay, you may do some division operation, addition operation, any kind of operation could be there. Okay, it could be any operation. So you might aggregate it, aggregate results. Okay, aggregate. The keyword here is aggregate. It so solution of current problem. It depends on smaller sub problems which are independent. Okay, in that case, yeah, you can represent that into some recurrence relationship, and once you end up with this recurrence relationship, you can think in direction of DP. Yet we didn't cover DP, but I'm just telling that it is start of DP. You need to be able to build those recurrence relationships. If you can build that, then DP is cakewalk for you. Okay, DP is cakewalk once you do this. You just need to create that. And how will you end up with this? So there are a few things which you need to keep in mind. You need to do few observations, and after that you will be able to end up with recurrence relationship. I will take example for that, and you will be able to better understand it. But for now, we'll see that our Fibonacci problem, why we need DP for that. Okay. So what is the problem with recursion, right? Why are we seeking out for some other solution when recursion was just perfectly fucking fine? So our recursion solution, how it works. Let's see into that. So let's say I want to find the Fibonacci sequence, fourth number in Fibonacci sequence. How will I be able to find it? So can I say that it's nothing but f of 3 plus f of 2? Okay, I'm just following that recurrence relationship, this one. So yeah, I can say this. But to find f of 4, I need f of 3. Okay, no issues, I will find f of 3. For that, can I say it will be like f of 2 plus f of 1? Okay, that's also okay, but I will need f of 2. Okay, you go ahead and find f of 2. So f of 2 is nothing but f of 1 plus f of 0. Now f of 1 and f of 0 we do have. Okay, it's going to be fixed value, we know that. And from in this problem you need f of 2. So you will again find f of 2, although you have this thing here, but that's what I was trying to say. If you will try to visualize it in form of tree, how things would go there. So let's see that. So let's say I want to find for f of 4. Okay, I will call for f of 3. Okay, I will also call for f of 2. Again, then I will call for I minus 1 and I minus 2. Okay, I called for f of 3. Now this branch will be completed first, right? That thing we know. So yeah, it will call f of 2. Again, I minus 1. And later it may call f of 1 as well. Okay, but now in this branch we will proceed. So yeah, it will call f of 1. Okay, after that it might call f of 0 as well. Okay, it might call after that. Now f of 1 is our base condition, f of 0 is base condition as well. We know that what actual value is there. Anyways, yeah, f of 1 here again is base value, so something will be returned there. So I can say that this f of 1 is guaranteed to return 1 to it, 1 to this function. It will call for f of 0, it's going to return 0. Can I say summation of this two is what f of 2 will return? So 1 plus 0, 1, it will be returned there. Okay, that's cool. Now f of 3 would have called for f of 1. F of 1 would return 1, its base case. Okay, now f of 3 has 1 and 1. It will get add up and 2 will be returned. Now f of 4 would have called for f of 2. Okay, f of 2, again f of 2 would call for f of 1 and f of 0. Okay, first of all, f of 1 will be evaluated, or that specific call will be handled by our program. So f of 1 will return 1. Okay, f of 0, it's going to return 0 itself. Now f of 2 will take some of them and return. So I can say that 1 will be returned. Now f of 4 has both of these values, 2 and 1. So can I say summation of them will be returned? So f of 4 will return 2 plus 1, which is 3. So this is how we get solution. And if we cross check, so 0th number, first number, second number, third number, and fourth number, we want fourth number, right? 0 and 1 we have. 0 plus 1, 1. 1 plus 1, 2. 1 plus 2, 3. So fourth number is 3, which we can see that it's correct here as well. Now comes main part, observation. Okay, because we need to optimize this, we will see for some observation here. So can I say that f of 4 called f of 3 and f of 3 called f of 2, okay, and f of 1 as well, but yeah, f of 2 is called here. Okay, f of 4's second call was for f of 2 only. However, we have called this f of 2 already, right? We are calling it again. It's okay that but we are calling it again. Okay, and that is actually increasing our time complexity if we think about it. Okay, in this case, if you see the time complexity from this tree, okay, in this tree, I can say that there are at most two branches for any of the nodes, right? This is a recurrence tree. I can say time complexity can go up to 2 to the power n, 2 to the power n, right? For every node, you have two options, okay, and that you are computing. So time complexity in terms of n, can I say it's going to be big O of 2 to the power n, right? Big O of 2 to the power n. Okay, because for every function you are calling two other function. Okay, so time complexity is going to be 2 to the power n. Okay, that's correct. Now, space complexity in this case, because it's a recursion call, I can say that it would be depth, and how deep it could be. So I can say that at any given point in time, its depth can be it's like big O of n only, right? Big O of n. So this is for recursive call stack. How deep this recurrence tree can be. Okay, time complexity is in exponential, right? Like it's very high. We might want to optimize it, and where we got hint for that, right? We are calculating the same problem again, or rather, I can say I am calling the same function, like I'm passing same argument in the function, and I'm calling that function again, and it doesn't make sense, right? You have already computed result of f2 and you are calling it again. So that is the problem which we've seen, and that's what we will fix, right? So in this case, we see that f of 2 is getting called twice. Now, this was case for f of 4. If we scale it up, maybe we do for f of 100 or something. Just imagine if you do for 100, 2 to the power 100. Okay, this many operations it will take. Okay, I know that 2 to the power 10. Okay, I can say that it's going to be around 1000 or something, right? 1028 or something like that. So I can do 2 to the power 10 and 10 like that, and 10 to the power 3 I can do. I'm just approximating it. So it's going to be 10 to the power of 30. These many operations. And I know that my compiler is probably going to allow me in 1 second 10 to the power of 7 operations at most. 10 to the power 7 is also a dangerous zone. It should be under 10 to the power 6 or something, right? So we need to optimize something. Just give me a minute, I'll check. Just cross check the value of 2 to the power 10, and yeah, it's 1024. So I can assume it as 1000, and it's going to be basically 10 to the power 3. And yeah, this rule of multiplication, so 10 to the power 30, it's going to be 10 to the power 7. Okay, this is our limit, and this is what we are getting. Just imagine, like, it will not pass your case, right? The ID will simply say your online judge ID, it will just simply say that time limit exceeded, or sometime it also will, give memory limit exceeded, because in this case, actually, you are using a lot of space as well. But any of these can come, and it could hinder the process. So what we can do is, why don't we store the results, right, which we are generating after every function call. Okay, and let's see how that helps us. So I will again draw the recurrence tree, but this time I will keep track of whatever I have computed. Okay, f of 4, and it will call f of 3. I can say that it's also going to call f of, or maybe let's just go with the flow only. Yeah, f of 4 will call f of 3, f of 3 will call f of 2, f of 2 will call f of 1. F of 1, we directly have value. Okay, it's going to be 1. 1 will be returned. F of 2 will also call 0, right? I minus 1 and I minus 2 will be called. F of 0, again directly we have value, which is 0. Our base case, that's what is written to f of 2. Okay, this f of 2. Now can I say that this result, I just won't return it directly, I will also save it somewhere. So I can use some sort of array here. Okay, let's assume some sort of array we have, and 0 1 2, let's say this function has this argument 2, right? So I can go in this 2 and I can store the result. Okay, then so that I can reuse it later. We'll see in code as well how that works. But for now, that's the case. So f of 2 will return 1. However, it's also stored in the array. Just see that magic how it works. So f of 3, now it will call f of 1 as well. We know that f of 1 will be called 1 again, our base case, so return 1. Okay, that's right. Now f of 3 will return 2. That we can store just before returning. Okay, return 2. Now f of 4, will it also call f of 2? I would say yeah, because I minus 1 is 3, I minus 2 is 2. It will call for f of 2. Now you will see that you already do have result for f of 2 already stored with you. So why recompute? Just give that here. Okay, so you will give that here, and your result which you had was 1, and it will return 3. So you can say that you have completely eliminated many computations. Now it might not be visible directly here. If I just scale up this tree to some f of 100 or something, you will be able to see that many times this, okay, many times you will be reusing your solution. Okay, let me just scale it to f of 6 just to show this thing. F of 6 will call f of 5. Okay, and f of 5 will call f of 4, f of 3, f of 2, and f of 1. That's okay, but f of 2 will call also f of 0. F of 0. Yeah, f of 3 will call f of 1. Okay, and f of 4 will also call f of 2. Again, just keep in mind this 2 is also getting called here. And because we are using memoization, I am not going to do that compilation, right? We will be reusing that. Just see how many calls we are saving. Now f of 5, that will call for 4, and I can also say it will be calling f of 3. Now just see f of 3 is also getting reused. Okay. Now f of 6, it will call for 5, I minus 1, I minus 2, it will call for f of 4. Okay, again f of 4 as well you are using. Just imagine these many calls you have saved. If you would have not stored the result of 4, this whole tree, I would just copy paste this tree. So you will be able to see this whole tree would have been recalculated here. Okay, this full tree would have been there. So just imagine many number of computations you have saved. So can I say that for every of this value from 1 to n, I'm just computing one time, at max one time. So that helps me to find the time complexity as well. If I have n, okay, I want to find the nth uh, number in Fibonacci sequence. If I consider zero based indexing, it's just going to be big O of n. Okay, because at max for each call, we are just computing one time. So from 1 to n or 0 to n rather, we have this function call only one time. And for 0 and 1, we do have base condition. That's different thing. But yeah, at max n times you are calling. For space, still you are doing recursion and you will go in depth. At least you can see in this case we have this much depth. If I just mark the depth, you have n depth. So yeah, big O of n you have for recursion. Still you have that. However, because you have saved the result somewhere as well, that also would be some container in which you stored. Okay, as we discussed here, we generally use array for this. Okay, but later you will also see that sometimes we use hash maps as well. But for now, just think simply, we are using this extra container to store the pre-computed results or other previously computed results. So yeah, array. So in this case, you can see that we almost linearized the time complexity from exponential to linear. Now, if you want to find, as we discussed here, okay, n is 100. Okay, n is 100 in this case, and if now you would try it, it will fit. So it will be less than 10 to the power of 7. So it will work under 1 second in any online judge or any OA platform for which you are giving your interview. Yeah, it would just work fine in this case. So it's called memoization. We will see its code, that how we will achieve that in code. So memoization. That's what we call this. Okay, and it's not true DP. There's one more thing to it, which is going to be tabulation. We will learn about it, and we also sometimes do space optimization. However, from interview perspective, it's not as much expected, but definitely we'll look into it. Sometimes you can show that solution as well. So yeah, introduction to DP. We already discussed what DP is. So now let's just write the code of Fibonacci sequence generation or finding ith number in Fibonacci. So just write your memoization code. Don't do any fancy stuff right now. Just memoization code. So can I say that okay, I'm just using a pseudo code here, pseudo code language here, but I hope everyone knows that how you could replicate it to C++, Java, Python, Rust, whatever language you are using. So yeah, fn, and I am taking some integer I. So this is basically ith number in sequence which you want to find. Yeah, that's what we are taking, and we will return some value from here, which is the actual value of that uh, ith number in sequence. Yeah, and as discussed before, it's just going to be like this, right? Return, call the function for I minus 1, call the function for I minus 2. Okay, generic recursion stuff. That's what you will do. Okay, you will definitely have some base condition here. So base condition simply would be like, okay, if you have I which is, you know, less than or equals to 1, then in that case you will just simply return whatever your I value is. So it will handle the case for 0 and 1. Okay, for now you can say that it's going to be 2 to the power n time complexity in terms of n. The time complexity is going to be big of 2 to the power n. Now to memoize this, okay, to memoize this, what small changes we will do? Just see, it's very small change. What we'll do here is with this I, we will also have some array passed, which will store the result as we discussed in this case. Uh, yeah, here this array we had, right? Generally, we call this array as DP itself. So yeah, that you pass. So it's an array only. Okay, and you pre-initialize your array with size to accommodate the I, right? So you will have that DP. Now what we'll do is, okay, this base condition will remain as it is. You will do simply I, if that is less than or equals to 1, return whatever the I is. That will remain as it is. Okay, and this return statement, okay, as discussed before, we will store whatever we have computed, right? So can I say that our DP at index this I, because we are storing for this argument what was the result of function call. So DP of I, and then same thing I will take which was here. So I will just simply take this thing and I will put it here. So what this will do is it will still compute this and it will store it here. So now you are storing what have you computed, but are you still using it? In this case, you will still be ending up with 2 to the power n calls. Now, if you have computed it, then use it. So what you will do is you will just write here an condition, which is going to be if dp of that index, your argument, in this case I, if that is not equals to minus 1. Minus 1, it's just an indicator that for this specific argument, you have not computed result for the function call, right? If it's not equals to minus 1, means you have computed it already. Then don't compute it again. Just return that thing. So I can say return dp of I. That's it. So this statement will not be called. You are directly returning from here, saving lots of calls. So this is like you can just count how many changes we did. Okay, we did this one liner change here, second line, third line. So this is like enhanced version of recursion only, and you can expect that if you end up with recursive relationship and you write code for recursion, just two three hardly changes you will need to do. and you will end up with the memoized code. And memoized codes are really fast and it's on par with tabulation. Hardly two, three problems are there where tabulation overpowers the memoization. And in practice, they both work like very similarly. Okay, memoization does use a little bit more of space, but I think that won't be a big issue in OS. However, for interviews, we definitely need tabulation. So we will also see that how we will, like tabulate it, but in a while. Now, first, let's come to how to identify DP problems. Okay, so for DP problems, as we discussed earlier as well, you need to first of all create your recurrence relationship for any problem given. So create a recurrence relationship, okay, and then see if in recursion tree, okay, you will not draw a whole tree. Just see that if you are able to see a case where you are recomputing something which you have already computed. So say if in recursion tree, if you are recomputing same state, okay, I'm just using a new word here, state. So it's just same function call you are doing. If so, just memorize it, right? Just one thing here, that ensure the problem is independent. Okay, that's very important thing. It should be independent, right? Problem is independent. What this means is that it should not depend on other sub problems, right? In this case, if you see in Fibonacci, so if I want to find for, let's say, yeah, here, let's say I want to find for f of 5. Okay, f of 5 depends on 4 and 3 because they are part of subproblem. But f of 5 doesn't depend on 6. F of 6 does depend on f of 6. F of 5, right? F of 6 depend on f of 5 or 4. But 5 and 4, okay, 4 can be solved without 5 or 6 influence, right? I can segregate those subproblems. So what here we'll do is, okay, in this case, ensure that problems are independent. And if so, then try to memorize it. Okay, so memorize it. That's what we will do. Now let's just quickly think how we will, like do the tabulation work, right? As I told that it's in real DP we do tabulation. So tabulation is like, here you will not use recursion. Totally iterative. You will have totally iterative solution here. No recursion will be here. So how will you convert that? So let me just quickly take our pseudocode of this memoized DP. Okay, so this was our memoization code. So keep in mind that your tabulation, okay, you will generate your code from memoization to tabulation or from recurrence relationship directly. So in tabulation, you need to keep few things in mind. That is, grow from base condition and build up, or what essentially that means is same, grow. So yeah, from smallest sub problem, you will use that smallest sub problem to solve bigger problems and on and on. So you will not end up with situation that for bigger problem you do that smaller problem and then again you need that. So you start itself from the smallest problem which could be solved. In this case, can I say that this is our base condition Okay, and if I do in this order, that I generate the 0th number, first number, second number, third number, and I go till I. I'm sure that would work for me, right? You can say that your memoization code just reverse of that, it would be in iterative code, right? So what I will do is, okay, I will write still I and dp here, okay, and just see how I'm making the changes. So yeah, from our base condition we will grow. So what I will do is I will just run a loop, okay, and let's say we have, maybe let's just keep dp here, because I anyways we will start from our base condition, right? So we don't need that in this call. So you can say I we have, it will start from 0. Why 0? Because that was our base condition, right? 0, 0 and 1, that were our base condition. So it will go from 0 and up till what? So we will pass here that thing which we want to find. So I will pass here, let's say that we want ith number, right? Let's just keep this variable name I and just change that to j, just a small variable name change. So yeah, j will range from 0 till I. Okay, it's inclusive. Till I we will go. Okay, and then here I'll just do what I did in this recursive call. Okay, I'll just say that if it is less than or equals to 1. So I will just say that if, okay, if j is less than or equals to 1, means our current computation, for that we have argument like ith in Fibonacci series, ith number. If that is 0 or 1, we are sure we know its solution. So what I will do is in our dp, okay, in our dp, for that jth index I will just simply store j. Okay, till now what we are doing, it's same as this recursion. Instead of returning, we are just storing here. We can't return, right? Because this is function call and it will end. We will see that how we will, skip that part of, yeah. So here we have this. Now, because you did this, we are sure that we don't need to look up for previous value. We can just continue, right? I'm sure that you are aware about this keyword, continue. Okay, what this does is that it will pass the loop, like it will be next iteration directly. So yeah, that thing, and then let me just take this down. Yeah, cool. So here we have this case handled. Now, in general case, what we were doing is we were returning this. So we'll not be returning this. Okay. What we will do instead is I just take this thing. We'll just set the value of that. So I will just paste it here. Yeah. dp of I we want to store it as, this time we will not call the function, right? We'll just do, because we know that it's previously computed, right? I'm sure that for dp of I have dp of I minus 1 already calculated. Okay, because we are starting from 0 to I. That fact allows us this. And again here I will just do dp of I minus 2. And that solves our problem. Okay. So here this specific part, you can write this with just 3 or 4 line change from memoization, and it will be tabulation. Now again, how we will return what you want, right? So here you will just write your return statement for dp of I. Okay, and in this case these all should be j only. J, yeah, j minus 1, j minus 2. So you will return for dp of I for the one which you want. Now I will just show you one more thing here, space optimization. Space optimization. Okay, it's rarely used, but it's good to know. So yeah, in this case, just look at this code and tell me if you can see a catch here, some optimization catch here. So can I say that for any given I just want its previous value and second previous value? Do I need third previous value, fourth previous value, or anything till like 0? I would say that I do not need that. So can I just, instead of using this whole DP array, Can't I just use two variables here, like previous and second previous, and that would just help to solve this in constant space, right? So what I will do is I will just take again this whole code and I will just show you how you can optimize it, right? So yeah, this is your tabulation code, right? Now you will not be using the DP here, no extra space or constant extra space, rather just two variables which we will have. Okay, just count the number of change we did. We did one change here and here I'll just declare two variables. So int previous. Okay, now I would be able to write better. So yeah, int previous and second previous. Okay, these are the two variables we need. Now what I will do is, okay, now I will in this function call, I will add some extra space. Yeah, so here we will have this thing int current, right? Current state computation. Let's just make it as 0. It doesn't matter whatever we keep it. Instead of wherever you see dp of j current state, just do it like this. Okay, current equals to j. Okay, here dp of j, again you will just say current. Okay, and wherever you see dp of j minus 1, we know that it's previous. Just do it like this. Previous, previous. Okay, now wherever you see j minus 2, we know that it's second previous. So just remove it and add your second previous. Cool. Now, are we updating our previous and second previous? No, we are not updating it right now. So we should be able to update it. We should update it, right? So for that, you can do some minor changes here. Okay, I'll just do one thing. Okay, I'll just maybe let's just do it like this. I'll remove this continue here, continue statement, and in else we will do this because again we need to do the changes, right? So yeah, in the else statement we will do this. Okay, and after that I am sure that for updating what we can do is our second previous we will update first. So let me just bring this thing down as well. Yeah, so your sec second previous, can I say it would be previous, right? And your previous value, that would be what was your current computations value, right? That's what it would be. And then you can see current, it's a temporary variable only, right? So it won't matter much. So you can see that these number of changes we did, right? So again, I would say that yeah, here we had a few more changes. So it was like around 4 5 line changes. So you can see that we can just build from memoization. So the flow would be like this for any DB problem. You will do like this. First step would be find recurrence relationship. Okay, find recurrence relationship. What would be your second step? Your second step would be, let me just write it like this. Yeah, first step would be this. Second step would be code your recursion. Okay, third is memorize it. Fourth is tabulate it. And fifth is maybe space optimize if needed. Okay, maybe space optimize if needed. So yeah, your main challenge here just would be finding this recurrence relationship. After that, it's a happy flow that you will do your recursion code, you will do your memorization, and you will do your tabulation. Okay, and the space optimization, this won't be every time. This won't be the case every time. In few of the problems, it's not needed to space optimize. You will not be able to even find any space optimization. In some cases, you will. In most cases, you will be able to find it, but in most interviews, they are not. It's not expected. But again, we'll try to do that thing in almost all of the problems. So yeah, this is their four or five step frameworks. So a framework for solving an DP problem. Again, one more thing here is that this is mandatory step. So finding the recurrence relationship, and I would suggest that you go in this step. So in these steps only. However, once you build your experience, sometimes you can jump directly from your first step to fourth step. Okay, that's possible, but it comes with experience. And the main challenge which we have in DP problems is not all of these steps. We have problem when this finding the recurrence relationship. That would be like the most tough part. Okay, and it's not always the case that you will end up with this recurrence relationship. Like you will always be able to code for recursion and all, right? Sometimes it's not intuitive to build recursion, and sometimes you directly build a tabulation. We will see those cases where we have DP on grids, DP on grids of zeros and one or those pattern of questions where we don't generally think in direction of recursion, right? We just write our recurrence relationship and move to tabulation part directly instead of recursion because that becomes more intuitive. In LIS and some other variations as well, we directly go with tabulation and we just don't use recursion there. So there are few cases, but for now, we can generalize it as for basic questions of DP. We will follow this flow. We'll first of all find the recurrence relationship, then we'll code the recursion, then we'll memorize it, then we'll tabulate it and then maybe space optimization. And sometimes we also need to work on that grid, right? Which we make grid or like we have multi-dimensional DPs as well. We'll look into it. So the DP, this DP array which we created, right, for Fibonacci, sometimes we may also work on it. Okay, and that we will explore when we will go in depth for some some tougher patterns for DP of strings and all. And we sometimes use that grid to construct back our result or something. For now, it's high level for you, but yeah, that's the thing. So yeah, this was the basic introduction to DP, and then from next lecture we can move on to different patterns which we have in the DP. And just to give you an overview of those patterns, we have 1D DP, which we just discussed as well. We will have grid-based DP or multidimensional DP. Then we will have DP on subsets, DP on strings, LCS, lowest like longest common subsequence, and then we will have LIS, longest increasing subsequence. Then we have few special case of matrix DP, as I discussed, the zero ones and those kind of cases. And we do have few other patterns as well, digit DP and DP on trees. However, they are probably beyond scope of this course and are not asked in generally any interviews. So this was the basic introduction to that, and I have few problems for you which you can try at your home. So climbing stairs, you can do that. You can do house robber, and you can do minimum cost of climbing stairs. All of these are just easier versions of all of these are easy questions and are just wrapper around whatever we discussed today. Very easy question. You should be able to solve all of them. And yeah, this was the lecture. Let me know in feedbacks whatever you think about it or where should I improve and all.